Okay, so we're going to start with not compound. Yeah, compound inequality that we're going to go over right now when it comes to graphing the solution. So I'm just going to make up an inequality for us. So let's say we had 17 minus 5x, right, is less than or equal to 15 and is greater than, let's say, negative 3, okay? Now, here's one thing about how I just read this. This thing right here, whatever it is, I can call this even x, all right? If this was an x, whatever it might be, this is less than or equal to 15. If I read it the other way, 15 is greater than or equal to this. Those are the same sentence. Do you understand that those are the same sentence? Yeah. Okay, so that's important. You have to make sure you can read things frontwards and backwards, and that's what's messing up the graphing. You guys are doing weird things. If you're graphing, and if you pay attention, and I've never graphed anything in the way you're graphing something, where they're both going in the same direction and weirdly partly overlapping each other, you're messing up because I've never graphed anything like that before to show you, okay? So what we're going to do first is we want to get x by itself, all right? If we want to get x by itself, what should I do first to work on that? We want to isolate the x, subtract 17. So I'm going to subtract 17 from all three places. So minus 17, and minus 17. Negative 3, take away 17, and I'm left with negative 20. Less than symbol drops down. These are gone. Negative 5x is in the middle. Less than or equal to, what's left over here? Negative 2. Next, we have one more step to get the x alone. So we're going to do, Zach?
You would divide by negative 5.
And?
then you would flip those signs.
Right.
By
Good. We're dividing by a negative. We're going to have to flip our inequality. So divide by negative 5, all three places. So watch out for that. Negative over a negative. Something's wrong. No, that's fine. Negative over a negative, we have 4. Positive. Some of you are leaving negative over a negative. Don't do that, okay? In final answers with interval notation, when I was looking at the Google form, people are doing like bracket, negative 5 over negative 6, whatever the numbers were, comma something. Negative over negative, you make that positive, okay? This sign flips, so now it's greater than, and then x is alone, then this is greater than or equal to, and that becomes 2/5. So this step right here is, if we were only looking for an inequality as a solution, this is our answer. We're done. That's the inequality. The directions usually say, find the inequality, graph your solution. When I say graph the solution, look at the answer. Should I be drawing a y-axis? No, there's no y, it's just x. So we're only drawing a x-axis, also known as the number line. Now, pretend for a moment that this was 4/5. 2/5 and 4/5. Which one's bigger? Okay, if you were thinking 2/5, you need to regroup, okay? 4/5 is bigger than 2/5. Make sure if you know they have a common denominator, you just compare the numerators, all right? So in this case, which one's bigger, 4 or 2/5? 4 is bigger, good. So 4 goes here, 2/5 goes here. Do not just put them in the order that they're in on your paper. Now, I got a big open circle, marking each spot. Do not make it a mystery. If it's open-ended for me to grade, don't make me wonder if you are including that point or not, okay? So I'm going to look at a couple different things. One inequality part of this at a time, okay? First thing I have is x is, I'm going to do this one, x is greater than or equal to 2/5, right? Greater than or equal to 2/5. Which way from 2/5 am I supposed to be shading? Which way from the 2/5 should I be shading for this problem? To the right, good. And then for the other one, we'll do that one as well. There's a lot of issues happening with that one. So I'm going to just use a couple colors here. Okay. Here in yellow, I'll go from 2/5. This is colored in, right? And really, I would shade all the way this way. I'm not suggesting you shade that whole thing, but you see I'm shading in all of this, that whole direction. And it's a little hard. This yellow is not as bright as my other highlighter is. Okay? So it's all the way that way. Now, how do I read, and that's this piece over here. How do I read the other one? This one over here, read from the x. It's not my first time saying this. Not my second. Read from the x. How do I read from the x? How do I say this? Try to answer it in your head before someone else tells you. You can pretend you knew. X is what? Go ahead. X is less than 4. Yes. So here's 4. Is it colored in? No, only if it's or equal to. And x is less than 4 means I shade this way, like that. But this is a compound inequality. I want the answer where it's shaded twice. Anywhere the pink and yellow can coexist. Where do they coexist? Are they coexisting to the left of 2/5? At 2/5?
Oh, yes.
Yes, they do. Pink's right above it. I just did it above it, okay? Do they coexist between 2/5 and 4? Yes. Do they coexist at 4? No, only pink, pink starts right next to it, only yellow is there. So my answer is what's really shaded. So it's really a closed circle at 2/5. It's shaded in between, and then it's an open circle right there. So that is what we have going on right there, okay? Now, of course, it should be second nature. You got to just automatically write it down in interval notation. No hesitation. Don't even wonder if it's going to ask you to do it. Just do it. Interval notation. What would the interval notation be to answer this question? We go from left to right. We only talk about what is shaded by both of them, from left to right. Michael, what is it?
Bracket 2/5,
Perfect. Done. That's the answer right there. Bracket 2/5, comma 4, parentheses. This shaded region right over there. If I just put this on here again without the pink and the yellow, I don't suggest writing it like that. I would say just think about what it is and take care of that answer like that without doing two different shadings. It gets too confusing that way. So here, done. Interval notation. All right? So things to watch out for when you divide by a negative, you got to flip the sign. When you flip the sign, don't lose your little equals to, or don't add one when it doesn't exist. That was one thing a lot of you guys were doing. Okay? And when you flip the sign, it doesn't mean it flips like this goes here and that goes there. It means this flips itself and this flips itself. Okay? Any questions on this specific type? Going once, going twice. We're just going to clarify questions on number 3 over here because this is in the answer key video for the study guide, but just to clarify the optional step on here. If you want to go factor something like this is a 6th degree binomial, and we do not have a constant term. If you don't have a constant term, you probably have or you definitely have a what? G. There's no C on F, but no, you're not because you're going to use the greatest common factor, the GCF. Good. What's the greatest common factor to these two things? Negative. I like to take the negative when it starts with a negative. Negative 3. X, how much X can they spare? Good. So I'm going to factor out or undistribute a negative 3x to the 4th. When you factor that out, you're essentially dividing by negative 3x to the 4th. Okay? A little squished over there, but there it is. I'm dividing it out, and we do the little pretzel move to get what's inside. Okay? So you could still do this pretzel move that we do when we factor by grouping on something smaller. It's not a big deal. What ends up inside? What does this divide down to? 9x squared. And at first you might think like, ooh, 9x squared minus, it looks like the beginning of a difference of two squares, right? That's a perfect square difference, it's minus. But what's 39 over 3? 13. A little sad because it's not a perfect square. If this was a 16, you'd recognize it as a perfect square. If it were a 25, if it were a 4, but it's a 13. So really, if you left it like this, you're fine, okay? I would not take off points for something like this because it's not a perfect square. However, I did say in the video, optional step. You could still factor it as a difference of two squares. We're going to leave that out front. So negative 3x to the 4th. When we factor the difference of two squares, we factor using, say it, you're right there. Good, conjugates. We're factoring using conjugates. So the conjugates are not 9 and 13. You have to remember that optional step that a lot of you don't want to do. The optional step is what squared minus what squared. This is me putting on my glasses. Those are the glasses, okay? So if you have something like this, you're looking at it with x-ray vision over here, okay? This is you, and you're very happy to see what's being squared, okay? Do you understand the glasses? Yes? Good talk. So what's being squared to make 9x squared? If you look through this, look at the ingredients. 3x. Now, even though it's not a perfect square, I didn't need to write that there. What's being squared to make 13? Exactly, the square root of 13. So, sorry, I'm just going to erase this. Square root of 13. So this is 3x, and this is square root of 13 because it's not a perfect square. Isn't that the square root of 9, the square root of x squared, right? So those are the things we use when we're factoring. Those are the things we use to make our conjugates. I don't know how bright this will show up because I think some of my letters are kind of dark, but that 3x goes here, and then the radical 13 goes where? On the right side of each one, and conjugates means that their signs are one's subtraction and the other is addition, and that's it. Okay, so that's what goes in there, even though it's a little, different. That's okay. Different means love too. 3x, rad 13, and radical 13, and one is plus and one's minus. So again, I called this an optional step in the video because it's not perfect squares. I'm not trying to be a stickler, but it is going to be something you may end up doing in the future if you end up taking something like calculus, okay? Pausing, and we'll carry on in a second. So now we're going to talk about the difference or sum. Sum is addition, minus is subtraction, difference. So sum or difference of two cubes. Now, cubes, we might picture cubes like this. Now I want you to picture cubes like this as if they were made out of soap. These are soap cubes, okay? These are soap cubes, cubes of soap. You're staying at a fancy hotel, and they have a basket of little soaps by the sink, and they're a bunch of little cubes. When you see perfect cubes, I need you to picture this in your brain, okay? So here's your nose, your eyes. This is you smiling because you love to think about this in your head, okay? Scary, but this is you, all right? Now, what are some perfect cubes? That's you. What are some perfect cubes?
8.
So 1, 8, I heard 27. 64, let's not go in order. Okay, yeah, but like we're random order, guys. So like about 125 is next, then 216, 343, now 512, now 729, and 1000, 1221. Did I miss any? Oh. Who did I miss? What? 9 is 729. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. They're there. So these are all of them. This is 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed, 6 cubed, 7 cubed, 8 cubed, 9 cubed, 10 cubed, 11 cubed. That's all I really know. Okay, I'm done after that. I forget the rest. Okay, so those are cubes. When you see numbers like that, you need to recognize like, ooh, cubes, okay? Happy having used soap, okay? Don't eat soap. It'll say it's in its mouth. It's a little concerning. Okay, go ahead. You're right. Thank you. What did I write? 1221. Thank you. Brain dead. I did 121 and then like fused it with 1331. Thank you. Thank you. Thank you. Okay. So an example. Let's even use that one then. 1331 x cubed plus 343. You're gonna look at this and be like, ooh, I have the sum of two what? Perfect cubes. So what is being cubed? So again, kind of extra revision this. What's being cubed? 11x and 7. This could be something you just think inside your head, okay? Or this should be something, if you're not as strong, this could be something that you actually write down, okay? So it's up to you. Next step, when you factor the sum of two cubes, we have one factor that's a B word, binomial, and one factor that's a trinomial. Then here, I'm going to take the 3's, we put them in our pocket, save them for later. And this helps us just cheaply build our binomial. So what's the binomial going to be? 11x plus 7. Done. Then, again, these are not like the real method. It's just a cheap trick. What cheap trick works to get the rest of this? Well, those 3's that we put in our pocket, we're going to sprinkle fairy dust. What's 11x times 11x? 121x squared. Good. Next part of the cheap trick. What is 11x times 7? 77x. Next, what is 7 times 7? 49. Again, this is not what's happening. It's just a cheap trick. Now, these are called soap problems for some of us, okay? We might call them soap examples. For these, what does SOAP stand for? Okay, same. Same as what? Same as the original problem. Opposite of the one before it, and always plus, always positive, whatever. You are done. This does not factor any further, okay? This is a prime. What's the other word for this type of an expression? A prime quadratic. Okay, you can call it trinomial.
Sum of squares.
A sum of squares. We have only difference of squares, really. There is a way. I mean, I could just show you quickly. You'll see it in the future. But if I had the sum of squares, like for example, 4x squared plus 25, right? That's the sum of squares. However, the rule we have is for difference. You guys did not use imaginary numbers in Algebra 1? I? No, right? I don't think you did. So we're going to do I in an upcoming unit. So quick, like, mini lesson. I'm not going to make you do this, but just to show you. If I ask you, like, what's the square root of 9, you guys could tell me 3, right? This is not the full lesson. It's just, like, again, a cheap, like, watered down lesson. If I ask you what's the square root of -9, the answer is actually, it's 3, but it's not real. So we call it 3i because it's imaginary. We actually need imaginary numbers because, like, when we build equations or solve equations, that might model certain behaviors and certain types of curves, or when we're using vectors in three-dimensional space. So, for example, people who work at those like control tower for airports, for airlines, they need to know exactly where a plane is. So, where on the ground, you can't have two cars in the same place, you'll crash. But if you're doing like GPS, sometimes your GPS doesn't know your altitude, so it looks like you're on another road and they get confused. Well, with planes, we can't have any confusion. Like, they need to know the altitude of the plane and everything, so they do use these imaginary numbers, even though it sounds made up. So we use these for things like that. So, side thing, I would change this into a difference of two squares by rewriting plus 25 as what? Usually we go the other way. We usually would have minus something and we would change it to plus. Minus, yes, no, minus negative. So is that still plus, right? So now is it the difference of two squares? Well, I'm going to draw a square on it, get it? So am I really finding the difference of two squares? Let's see. Putting on my glasses, what's being squared to make these things? What's being squared to make 4x squared? What's being squared to make -25? Good, 5i. You basically take the square root of it. I know, I'm not gonna make you do it, it's just, so this is getting your palate wet, like preparing you, dipping your toe in the water. So then you would just do 2x plus 5i and 2x minus 5i. Again, I'm not gonna make you, but you'd ask about the sum of two squares. What we use is something called complex. When we have imaginary numbers involved, we call them complex conjugates. That's all. But, ooh, I cut this off, I'm sorry. So say it again.
So you can't do sum of two squares?
You can when you do it like this, but they're just not real numbers. Now you're dealing with imaginary numbers. So it's in the complex number plane. It's something we use in vectors in like higher levels of algebra 2, which we're working towards. So we'll see that later in the future, but I'm not making you do that now. We're just doing fundamentals.
So on a test, if the final solution was a sum of two squares, we just leave it?
For now, you would say it's prime. Yeah. If it was a sum of two cubes, you could factor it. Sum of two squares, you say it's prime. You finish. You don't have to. And if you did do this, I mean, great. Maybe I'll give you a bonus point. So if like sometimes things factor to have a sum of two squares, you've seen them. So for example, even what if I gave x to the fourth minus, I think I might have done this yesterday with somebody, 13x squared plus 36. Okay? I can give an example like that versus x to the fourth plus 5x squared minus 36. Okay. If I gave this example, we can factor it the way we factor quadratics. We're going to do AC method and grouping. That works as long as we have a trinomial and this power is double that power. Usually we have a 2 and 1. So 1 times 36 is 36. What multiplies to give us 36? 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6. But b has to equal negative 13. Which pair? Good. So then I'll have x to the 4 minus 4x squared, because it's breaking this up, minus 9x squared plus 36. What's the greatest common factor of these two? X squared. What's the greatest common factor of these two? Negative 9. Bring out front, x squared. What's left? X squared minus 4. Bring out the negative 9. What's left? They match, so we're good. Now, I'm just going to go over here. I should have given myself more room, but bring the x squared minus 4 out front. What's left? X squared minus 9. Are you done? No. I have two difference of two squares. This one becomes x minus 2 and x. Good. And this one is x plus 3 and good. This one is similar. But you see, like, multiplies to 36, but gives us 5 in the middle.
If you had like x squared minus 4 and then x squared like plus like
9.
like plus 13, minus 13 as an example, where one of them was perfect square and the other one wasn't.
You could either leave it, or you could do what I did in that last example where it's like optional.
Can you do the perfect square for like 11
Yeah.
and put like x squared?
Yeah. So I'm going to skip a couple steps on this one, but when it factors, you end up with x squared minus 4 and x squared plus 9. You could just leave that as it is. You don't have to do anything else with it, and then you factor this one and leave that one. Do you understand? So it's the sum of two squares. So that one is x plus 2x minus 2, and this stays just x squared plus 9. So you could just leave it, and you're done. But if that was x cubed plus 8, well, then you could factor it. Okay? Question? Wait, was there anything else, though? So question, can I just do one more fast one out loud with you guys? Yes?
The degree name, or the name when the degree goes to the
Sixth degree. You just stop there. And then on the answer key, I wrote fifth degree instead of quintic, but I was like watching football and I mean that's why I wasn't paying attention. So just another quick one. Let's say I have, what do I want here? Whatever. 8x cubed minus 27. What's being cubed make each? What's this? 2x, thank you. 2x, what's here? 3. Guys, I was trying to do this quickly with you, so help me out here. This is another one, make sure we got it. What, take away the 3's, what goes here? Okay, then what goes here in your head? First term would be? 4x. Good. Middle term? We'll do the signs last. 6x. Last term? 9. Plus or minus? Done. Okay, finished. That's it. Got it? So that was another sum and difference of cubes. If we're doing domain from equations, it's one of the harder concepts that we're working with over here, okay? When you do domain from a table of values, when you do domain from a mapping diagram, or from a set of ordered pairs, it's pretty easy, right? To do the domain, you're listing the x's. To do the domain, this is a little harder. Easy, harder, easy, more difficult, easy, easy, right? Certain types of examples are easier or harder than others. I get that equations are going to be a little more challenging for people, but what kind of equation did I just sketch? Say it again, go ahead. Linear, good. Then is this still a linear equation? Is this still a linear equation? All right, is this still a linear equation? Are these all functions? Okay, if I give you any linear function, if it's a function, I'm allowed to, instead of calling it y, I'm allowed to call it? Yes, f of x. If f of x is a linear equation, a linear function, what does a linear function look like when it's solved for y? What form is it in? Give me an example of one.
2x plus 7.
Sure, 2x plus 7. What style is this linear equation in? What did you call this back in middle school? Sure, slope intercept form. Mx plus b. Some books use ax plus b because they just go in alphabetical order. Okay? M is your slope. I really shouldn't use an equal sign for that, but M is your slope and b is your y-intercept, right? All of these are linear functions. What is the domain of all of these linear functions? Negative infinity to infinity. So do you even have to think, next time you have a linear function, what's the domain? That's it. Okay? Next level, boost it up a degree. G of x. What's the next degree up from a linear? It's a quadratic. What does a quadratic function look like? What does it have to have? It has to have x squared in it, yes. So it has to have x squared in it. We derive the parent function with x squared. Now it could be any form of ax squared plus bx plus c. Examples could be something like 3x squared, just that, or 4x squared plus 5, or 5x squared plus 6x, or 7x squared plus 8x plus 9, right? Still all the same? All good? Or I could have something like, so these are all just examples, they're all quadratic, negative 10x squared. And I could do all these styles again with negatives in front. What does a quadratic function look like? Parabola is the name of the graph. It has this U shape to it. They can be more narrow. The vertex can move over. It could be opening downward. What is the domain of all of these parabolas? You have these arrows. It gets wide forever and ever. What is the domain? Yes, every parabola, the domain is still negative infinity to infinity. So you don't even have to think. You don't have to turn your thinking cap on. Just memorize it. Go ahead.
So like something that's a cubic function, I know that it like curves. Are we supposed to assume that it continues to curve, or does it just?
It doesn't matter whether right now for the domain, sometimes having you do range right now. So polynomial of degree 3 or more, right? Degree greater than or equal to 3. So yeah, they're going to just bend more. It might look like that. It might look like this. Okay, maybe it looks like that instead. Maybe it looks like that. Is it getting wide forever and ever? Yeah. Is there a hole in it? Any open circles? Any asymptotes? Any breaks? Jumps in it? Anything? No. So what's the domain for every single one of these? Yeah. So when you see any polynomial, you don't even have to think. You need to know the domain for these is always going to be negative infinity to infinity. However, when does our domain start to get hairy? Our domain starts getting a little dicey when we're dealing with fractions. Yeah. So say I have h of x equals, now this could be anything. I can put in Jen's equation 2x plus 7 up top. You're fine. You're living freely. No big deal. But what if I have like 4x plus 5 on bottom? The thing on the bottom of a fraction is what operation is being done with that? Division. What are we not allowed to divide by? Right. Not allowed to divide by 0. How do I make sure I don't? Well, I have to find out what, because x is a wild card. I don't know what x is. What number will make this equal 0? Do you have to just guess and stare at it with your superpowers? No. You use algebra. You say 4x plus 5 is not allowed to equal 0. This is not allowed to be 0, the whole bottom. Now solve for x like you're solving for x. Get x alone. Subtract. Subtract 5.
Oh, sorry. I won't.
Go.
I will.
Oh, I thought you were saying like as if I said no.
No, I will.
X is not equal to, so this is what I was talking about yesterday. Your parents tell you, I don't care who you hang out with, you just cannot hang out with that negative 5 over 4. He's bad news bears. I saw him shoplifting at the Walgreens the other day. He stole gummy bears. I don't want you hanging out with that kind of kid. Who can I hang out with then? I don't care. Anybody else. Please don't hang out with negative 5 over 4. He steals ShopRite. He steals gummy bears from ShopRite, from Walgreens, from wherever, okay? Bad news. So if I can't equal negative 5 over 4, your domain is everyone else you can hang out with. Who can you hang out with? All of these numbers and all of those numbers, right? And we need to color that. So, so what's the domain? What do I write down? What's the domain? From negative infinity until? Use a union symbol. Over until? Good, and you're done. The only thing you can't have is the thing that makes the bottom equal 0. You do not guess in your brain what makes it 0. You use algebra. You set the bottom not equal to 0 and solve for what x cannot be. Similarly, there's another one that has a rule that kind of causes problems for us. What's the other kind of example? When you have what other example did I give you on the study guide? Right, a square root. So make up something for our radicand. Let's put radicand is the name of the thing we put inside a radical. So that's a radicand, 2x plus 7. Now, what are we not allowed to take the square root of? What kind of numbers are you not allowed to take the square root of? Negative. Okay, on the flip side, so negatives are out. What can you take the square root of? What else? Positives and? Who's not positive or negative? Yes, positives and 0. Those are good, right? So your radicand, which is this, do you see what your radicand is? The thing under the radical, okay? Your radicand has to be positive or 0. Do I know a way to write an algebraic equation that will help me find when my radicand is positive or 0? Set it equal to 0? How, what? Right, greater than. Isn't greater than 0 positive? What's greater than 0 mean? Positive, yeah. Greater than or equal to which number? 0. Then you solve for x, done. So 2x is got to be greater than or equal to what? Negative 7 divided by 2. X has got to be greater than or equal to negative 7 over 2. Stop making decimals and mixed numbers. This is so beautiful. Let this be the way it is. Now, maybe before you do your interval notation, you do a number line. I'm a big fan of the number line. Here's negative 7 over 2. Which way do we shade? Which way do we shade? Greater than or equal to negative 7 over 2. To the right. Equal is colored in. Greater, that's all that way. What's the solution? As our domain. This is our domain. We're just connecting. When you've learned anything ever and you are supposed to know it, you have to be able to connect anything you learned in the past with newer things. Okay? That is like a true testament of who understands something. Make sure you're always prepared to connect concepts. You can't just be a robot and only know what you're specifically told you'll need to know. You have to build. You have to get improved. You have to get better. So what's the domain going to be? Bracket, negative 7 over 2. Good. To infinity, and infinity always gets parentheses. And that's it. Okay?
So that's with any square root, as long as it's not negative.
For right now, yeah. So we're dealing with square roots and simple radicals. As the year progresses, we're going to have things that are going to get more intense. Right now, we're at like the diet level.
And all quadratics, no matter what, are...
All polynomials. So quadratic qualifies.
So, and then for number 4...
Go ahead, explain. Oh, well, what kind of equation is it? The one you're looking at. It's linear. Even though there's a fraction, don't let the fact that there's a fraction fool you. Can't I have a linear equation y equals 5 over 8x plus 2 over 11?
Sure, but like that would still
Those
be
are not the
negative.
problem fractions. An issue with fractions is when x, which is the wild card, I don't know what's going in for x, when x is in a denominator.
Yeah,
That's when you have a problem.
so that's what we would do.
Because you
like,
can't divide by 0. Am I
7.
dividing by 0 here? No, I'm dividing by 8. I'm dividing by 11.
So that would just be negative infinity.
Yep. Yep. Another like sneaky one, and again, these could be extra credit questions I could ask you. If I made the bottom something like x squared plus 4, will this bottom ever equal 0? Why not? What's the smallest x squared could ever be? X squared, just on its own, x squared. 0. Who said 0? 0 somewhere? 0. 0 squared is 0. Any negative squared and any positive squared is going to be what kind of number? Positive, but 0 squared is 0. 0 plus 4 is 4. That bottom will never equal 0. So what would the domain be? There's no number that will cause me problems. Negative infinity to positive infinity. This will never have a 0 on bottom. Okay, no matter what the numerator is, okay, you'll never get a negative in your 0 in your denominator, sorry. So your domain is negative infinity to infinity. There was something else I just thought of, and now I don't remember what I was going to say. Oh, just this little thing. I've written this down before, but it's always handy to see. 1 over 0 versus 0 over 1. Do you remember me saying something? Was that in here? If you have a 1 over 0 or a number over 0, no, undefined. If you have 0 over 1, that's okay, because that equals 0. Okay? 0 on top? Okay. 0 on bottom? No. Got it?